Hello everyone and welcome to another PAT Problems video. My name's Helena, I'm the Access and Outreach Manager for the Department of Materials here at the University of Oxford, and today we're going to be taking a look at question number 12 from the 2015 PAT paper. So in this video series this summer we are going to be taking a look at questions from the 2015 PAT paper which could easily translate themselves into the new multiple choice format, which is going to be the format of this year's PAT paper. So this is the case with this particular 3-mark question, so let's take a look and see what it's asking. So in this question we have an ice cube sliding down a frictionless slope which is at an angle of alpha to the horizontal. Okay, so as I'm reading this, I'm instantly wanting to draw a diagram. So let's get started with that. So we have our slope at an angle alpha to the horizontal here. We're told that this slope sits on a horizontal table, so this is on a table, of height capital H above the ground here. If the ice cube is released from rest, so we have an initial velocity of 0, from a height lowercase h above the ground, so this full distance here is our h, what is the speed of the cube when it is halfway down the slope? Okay, so halfway down the slope, we have our ice cube in a position here. Let's call this position A and this position B, and it's now moving at a speed v, which we're being asked to find. All right, so let's have a look at a few more distances on this diagram. If we look at the distances between the slope and the table, we can see that this distance here is lowercase h minus uppercase h, never mind over 2 there. That's the next distance, getting ahead of myself. And halfway down the slope is now this distance x, which is now our h minus h over 2. There we go. So we're halfway down the slope at position B. Now, the way that I think I'm going to approach this question is to think about energy and how energy is transferred through this motion. Okay, so we're going to start off with some gravitational potential energy, and through this motion, some of that is going to be converted to kinetic energy, but not all of it. We're still going to have some gravitational potential energy because we're still a certain distance above the ground. Now, there's two slightly different ways of doing the solution for this question, depending on where you set your ground level to be, so your 0 of gravitational potential energy. You could choose it to be the actual ground here, or you could even choose it to be at the level of the table here, which is actually what I did when I first started attempting this question. So I'll show you how it works for both options, depending on which one you find easiest to do. So we'll start with approach 1, which is using the actual ground as our 0 of gravitational potential energy. Okay, so let's think about that. So like I say, we're starting off with some gravitational potential energy, and that's being converted into still some gravitational potential energy, but now we've got some velocity, so we've got some kinetic energy here. So if we use distances, heights above the actual ground here, our initial gravitational potential energy is mgh, and that is equal to mg, now we're halfway down the slope, which is a distance of h minus h over 2 plus capital H, plus our half mv squared for our kinetic energy here. Now let's just quickly rewrite this to make it easy to work with the bracket here, like this, which simplifies to h plus h over 2. There we go. Okay, so equating these two and starting to simplify, we have mgh is equal to mg h plus h over 2 plus a half mv squared. So I am going to cancel the masses. Luckily, we don't need to know the masses, which is good because we haven't been given one. And I'm also going to divide through by g. Just helps me organize things a little bit better. Okay, so now I'm going to move all these expressions over to the left so that we're left with the term containing the v on one side. So if we do that, we have h minus h over 2 minus capital H over 2 is equal to a half v squared over g. Okay, simplifying this side, we can see that we're left with h minus h now over 2, which is equal to a half v squared over g, multiplying by 2, and also multiplying by g. Over here, we get an expression for v squared, which, if we square root it, gives us the expression that we want for our speed when the ice cube is halfway down the slope. Okay. If we were to choose the table as our zero for the gravitational potential energy, we still do the same. We're just using different distances this time. Okay, so for this, we would have an initial gravitational potential energy of mg h minus h, because it's the height above the table. And then similarly, we would have mg h minus h over 2 as our distance here when it's halfway down the slope, and still plus our half mv squared. So just slightly different expressions for the distance. We do exactly the same method, exactly the same rearranging for v, and we get the exact same expression there. So that's two slightly different methods to solve this question. The only difference between this version of the question and the version of the question you might get in this year's PATS paper is there might be a few different options for this expression of v, and you just have to select the correct one from those multiple choice options. But otherwise, this is a nice example of the sort of question that might be on the multiple choice paper this year, and a couple of different methods of how you might go about solving that. So I hope that was useful. Thank you very much for watching, and please tune in for another PAT Problems video next time.